Hey guys, how's it going? So welcome to lesson 2.7 of our second unit. That is force in motion, and this lesson is on gravity and gravitational acceleration. So our essential question is, where does gravity come from? What is it? Where does it come from? So the fundamental first, idea of gravity came from Sir Isaac Newton. It's said that one day Newton was sitting underneath a tree, I guess relaxing, reading, whatever, studying, and an apple fell from the tree and hit him on his head. And he realized at that point that some force, something must be acting on these objects. Otherwise, they would stop. They wouldn't fall from rest. And that was in 1665. That was his first concept of gravity. And people went on to investigate this further, but really, Isaac Newton was the first guy to come up with the law of gravity. And then Einstein made the next biggest contribution, and he said that gravity really isn't a force at all. It's more as a curvature of time and space caused by mass and energy, and that is his general um, law of relativity. And we'll look at that maybe a little bit further. So, what is gravity? What do we know about gravity so far? Well, gravity is a force that attracts a body toward the center of the earth or the center of the mass toward any other physical body having mass. And it is caused by the warp of space time. And that always sounds super, like, almost extraterrestrial to my students, but it's quite interesting. So, the fabric of space time is commonly brought up in TV shows and stuff, but no one really knows what it is. It is a literally like a fabric, and it sits across space. And space is multi-dimensional, and objects that have mass sit on this fabric of space-time, this dimension, and it warps that dimension, and it pulls other objects to it. And if you think of it like, sitting on a piece of fabric or putting an object towards a piece of fabric or a mattress or whatever you want to think of, the heavier the object, the more mass that object has, the more matter it contains, the more indentation it's going to make in that fabric. So that's what it is. It exists everywhere in the universe, this space time, and the more mass an object that's sitting in it has, like a planet, um, there'll be a greater warp with that space-time, a greater indentation, and objects that are around that indentation. If you've ever, had some loose change in your pocket and it fell out when you were sitting on the bed, it always gets pulled to you, right? Because of the indentation you're making in the bed. It's the same thing. Planets orbit these other planets or stars or things in the solar system because they are pulled into that warp inside of space-time. So it's kind of complicated, but it's pretty interesting when you really think about it. It's like a fabric that sits across space because it's dimensionality, and that causes other objects to be pulled to it. The closer you are to that body, the the more you're going to be pulled towards its center of mass. We're going to talk about that a little bit later on. So gravity, while it's the weakest force of our other three fundamental forces, and we're not going to really cover that, that's more of a physics topic, um, it often takes over and becomes a more dominating force in an object's motion because it, whenever it's at such a scale, like the scale of me on the Earth, gravity is always going to dominate because it's such a larger force in that scale. So um, if we look at the different planets, we want to know why we have more gravity or less gravity on other planets. If you've ever heard of people visiting the moon, they say they kind of can jump and it takes seconds to land on the moon, right? If you jump up in the air, it's like you're floating. Or if you're out in space, there's zero gravity, meaning you can just kind of float around. Well, That's all because of your position relative to that large body of mass, and also the size of that body of mass. So if we look at these different planets, like Earth or even Jupiter or maybe the moon, you're going to have a different pull on you, force of gravity, depending upon what planet you're on. And that's because the gravitational acceleration of the planet is dependent upon the mass of that planet. The larger the planet, the greater warp in space-time, therefore the greater pull it's going to have on you. Remember, think back to the sitting on the mattress, sitting on the bed thing. The bigger the object put on the bed, if I put a tennis ball on the bed, it's not going to make quite an indentation. Other objects aren't going to be pulled to it. It's not like the pillow is going to be sucked to the tennis ball, right? But if I sit on the bed, and I set the tennis ball a little bit away from me on the bed, unless you have a really good like Tempur-Pedic mattress, the tennis ball is often going to come towards you. It's going to move towards you. And think of planets as the same way. They all sit on this fabric of space-time out in space. And you have Jupiter over here, and its moons, all the moons that are orbiting around Jupiter, it's going to have a greater effect on those moons than the moon is going to have on Jupiter. That's why those planets orbit the moon or orbit Jupiter. That's why those moons orbit Jupiter, sorry. And if you look at the moon in comparison to the sun is much larger than the Earth. So the Earth is going to orbit the sun. It's not going to be the sun orbiting the Earth. So you're going to have different, just like if you were one of those planets, you would have a different pull on you depending upon what planet you came in contact with, because it depends on that planet's mass. So actually, if you go to Jupiter, you're going to be accelerating at Jupiter because of its gravitational pull, 2, nearly 3 times faster than you would be at Earth. And that's going to cause you to actually weigh more because we're pulled on these planets, and that contributes to our weight along with the mass that makes up our body. So if you go to Jupiter and you weigh 100 pounds on Earth, you weigh 253 pounds on Jupiter. That's because Jupiter is pulling on you so much faster, and you're accelerating so much faster at the center of mass of Jupiter than you are at the Earth. And likewise, on the moon, you're only going to weigh 17 pounds on the moon because the moon is such a smaller body than the Earth, and it's going to pull on you so much less. Again, think of the sitting on a mattress thing, getting pulled in different directions. The greater the body of mass, the greater that the other objects are going to accelerate at it. So if we want to look at the different weights you're going to have at different planets, we're often going to look at the different accelerations on these planets. So the gravitational acceleration, or the acceleration due to gravity, is going to change depending upon the planet that you are on. So if you look at all these different planets, you can see their gravitational acceleration. Now, the gravitational acceleration on Earth is 9.8 meters per second squared. This is how fast we are accelerating at the Earth when we are at its surface level, the closest we can be to the Earth. Now, if I was on Mercury, it'd only be 3.5. If I was on Jupiter, it'd be 25.9. Actually, you accelerate so fast at Jupiter that you couldn't even stand on Jupiter. It would just crush you. That's the strength that you are going to be pulled at Jupiter. That's the acceleration you're going to accelerate at Jupiter. Think about if you jumped out of a plane, you were going skydiving. You probably wouldn't even have time to pull your chute. It's not going to be like here on Earth. You're going to accelerate multiple times faster at Jupiter than you're going to at Earth, especially when you look at the exponential part of that equation. So that is the equation right there. Force is equal to mass of the object multiplied by the acceleration of the planet. That is the force of gravity you're going to have on each of these planets. Okay, that's the equation that you will use to solve for the gravitational force. If you want to know what you might, what force you might feel on these different planets. Here's a quick check of understanding. If I have a mass of 100 kilograms and I am standing on Mars, what is my force of gravity? Okay, solve that. You can use the calculator or whatever, and I'll put that. I'll link that in the episode. So which direction does gravity pull? Because this is a really, really important part, especially when we start looking into our force diagrams. What direction does gravity pull? Gravity always pulls towards the center of mass of the object that is applying the force. So if the Earth is applying the force of gravity on us, if it is pulling on us, we will be pulled towards the center of the Earth. Okay? So not up here, not at the surface level. We're going to be pulled towards the very center of the Earth. The center of mass is the average of the masses factored by their difference away from the reference point. So what you basically do is you find the density, the overall density of different parts of an object, and this is very complicated, but find the densities. If there's differences in densities, you take the overall mass, and then you have to calculate the distances across those masses to find the center of mass, and it comes from a certain it's factored by the distances from a reference point. So in the case of a hammer, the center of mass is not in the center. The center of mass is actually up by the mallet part of the hammer. So that will change. But if you have a uniform, object like as far as we know, the Earth, it's going to be dead center. Okay, so like a tennis ball, it'd be dead center. So it does depend on the mass and the density of the objects, but typically the center of the mass is on the center if the object has uniform density, meaning that the weight is kind of spread out, uniformly or evenly. So that is all I have for you. Next time we're going to go into air resistance and friction. But just remember, you have the force of gravity, and then you have gravitational acceleration. So don't get them confused. I want that to be very clear. Gravitational force is the mass of the object multiplied by the acceleration of the pulling body. And then your gravitational acceleration is how fast we are being pulled at that object, and it depends on the object's mass. So force of gravity measured in newtons, gravitational acceleration measured in meters per squared second. So meters per second squared, sorry. That's all I have for you guys today. It's a lot to handle, but you'll be fine. Next time we'll get into air resistance and friction. We're going to move into applied and normal forces. We'll do a little bit of simple machines, and then we're going to talk about force diagrams and how we get this all together and we start talking about the sum of forces and balance and unbalanced forces. All right, guys, that's all I have for you today. Take it easy.